Now, most of the lecture I'm going to give now is actually covered in Chapter 7 of this book, Efficient Secure Two-Party Protocols by Yehuda Linder and Karmit Chazai. And it's a new book published on Springer, and if you have online access to Springer, you can read it there, which covers two-party protocols. And a lot of what we learn here comes from the book, this part about Oblivious Transfer, the definitions that we studied yesterday, YARS protocol, some of the applications I'm going to discuss later today are described there. So I guess about 50% at least of what is going to be covered in the first 2 days of this winter school is also, it also appears in the book, actually in more depth. So if you want to go into this material and study it more carefully, the school can be an introduction, and the book is actually a good place to look where they cover these issues in a kind of a uniform way, so it's much easier to read it in the book than to look at different papers that use different notations. So the book makes things much clearer. So we're going to discuss one out of two Oblivious Transfer, which was defined yesterday. So we have two parties, a sender and a receiver. The sender has two inputs, say x0 and x1. The receiver has a single input bit, j, which is either 0 and 1. At the end of the protocol, the receiver should learn xj, that is x0 if j is 0 and x1 if j is 1, and the sender should learn anything. So the receiver shouldn't learn anything about, it should learn one of the x's, but nothing about the other x, and the sender should learn which input the receiver asked to learn. Now, depending on the variant, these inputs, the xi's, could be either bits or strings. Let's say that they're strings, but it doesn't matter too much. There are other variants of Oblivious Transfers. There are variants where you choose out of more than two items, one out of 4, one out of n. There are variants where the receiver doesn't have a concrete choice. He's not able to choose which item it learns. Just the sender has two inputs, and the receiver learns one of them randomly, without the receiver being able to decide which of them it wants to learn, without the sender learning which item the receiver learned. There are all kinds of variants. They're all kind of equivalent to each other to some degree. We're going to discuss this variant, which is important to us in the context of secure two-party computation. For instance, in the case of YARS protocol, we use them to learn the input values on the input wires. Now we're going to examine the protocols in the malicious setting, that is with malicious parties, and we're going to prove them secure in the standard model, that is without any random oracles. I haven't described what random oracles are, but okay, for those who know them, we're not going to use them here. And we want to get proof of security, which are full proofs in the sense of simultaneity, meaning that they're according to definitions given yesterday. And this is useful because once we prove a protocol to be secure according to these definitions, we can then use it as a black box in more complex protocols without having to care about the proof anymore. So if I prove a protocol to be secure according to the definitions of full simulatability, then later on I can forget about the proof of security of this protocol and use it as a black box in other more complex protocol, assuming that this first protocol is implemented by some oracle, which just gets the inputs and gives the outputs. So in the case of Oblivious Transfer, once I prove it to be secure in the sense of full simulatability, as we'll show here, then if we want to use it in another protocol, say in YARS protocol, we don't have to think about the, how Oblivious Transfer is implemented. We don't have to think about the proof of security and how it's going to be affected by the fact that the protocol is being used in a much larger protocol. We can just consider the Oblivious Transfer as a black box where there are two parties. One has two inputs, the other a single bit, and the second party learns one of the inputs of the first party. So we might have to work a little bit more to get this proof of security in this simultaneity notion, but it pays because then we can forget about the details of Oblivious Transfer and use it as a black box. Now there are more efficient versions of Oblivious Transfer. If we relax the requirements, say if we can, we allow to use random oracles, or we don't want security to be proved in the full notion. Now the protocols I'm going to show you today, they're going to take a constant number of instantiations per Oblivious Transfer, may say about 10, okay? 10 or 20, which is not that much. It might be that if you really want to use it for some important application, and you want to do, say, 100,000 Oblivious Transfers, then doing 10 or 20 exponentiations per Oblivious Transfer, or doing 1 or 2, it makes a lot of difference. So in these cases, you might try to think, maybe I can use the random oracle model or use some other notion of security. But at least for now, we're going to talk about the full notion of security, because as long as you don't use a lot of Oblivious Transfers, the efficiency seems to suffice. Okay, so why should we study Oblivious Transfer? So it was already mentioned a few times during the winter school. And Oblivious Transfer is one of the basic primitives used in secure computation. This is why we need it. Kilian showed that cryptography, as he said, can be based on Oblivious Transfer, meaning that Oblivious Transfer alone can be used to construct secure computation, secure against malicious adversaries. Oblivious Transfer alone can be used to construct non-interactive zero-knowledge proofs of states with the NLP. So it's very powerful. And by saying that Oblivious Transfer alone suffices for that, I mean that, okay, as we're going to show here, we describe Oblivious Transfer based on, say, the DDH problem, encryption, things like that, okay? But all of these are not necessary for doing secure computation. It's sufficient to have just Oblivious Transfer. I don't care how it's being implemented. Say by using DDH assumptions, say based on other assumptions, say using some quantum assumptions about the communication channels. There's also Oblivious Transfer of that sort. Say by some trusted hardware. Once you have Oblivious Transfer, you don't need any other type of cryptography, no encryption, no signatures, nothing. You can do secure computation. So it's really a basic primitive which enables you to do most of the things you want to do in secure computation. So this is why we studied it. Also, Oblivious Transfer is used extensively in secure computation. Often it is the bottleneck in terms of efficiency. So if we save, this is somehow related to what I said in the previous slide. Many times, most of the overhead of the secure computation is spent on doing the Oblivious Transfer. So if we improve the Oblivious Transfer overhead by, say, 20%, then the overhead of the entire protocol might be improved by something close to 20%. So it pays to pay close attention to Oblivious Transfer and try to make it as efficient as possible, or at least to try to understand exactly what we need there. So if it's such an important primitive, we want it to be as secure as possible. And most of the crypto we have today is based on computational assumptions, hardness assumptions, like the hardness of factoring, or the DDH problem, the decision of Diffie-Hellman problem. And these assumptions, we believe them now to be true, that it's hard to factor or hard to break the DDH assumption. But perhaps that's not the case. So it's better to have security in information theoretic sense, namely unconditional security that does not depend on any cryptographic assumption. So even if we have quantum computers and maybe infinite computation powers, the protocol will still be secure. So for an important primitive like Oblivious Transfer, it seems tempting to look for an Oblivious Transfer protocol which is unconditionally secure. Doesn't depend on any computational assumption. Unfortunately, this is not possible. And I'll show you now in a few minutes why it's not possible, so therefore we have to resort to protocols which are based on hardness assumptions. I'll show this by showing that there is no secure protocol for computing the end functionality. There's no secure protocol for the end functionality which has unconditional security. And then I'll argue that this implies that there is no such protocol for computing oblivious transfer. So the end functionality is a simple functionality, the one you can think of. There are two parties, each of them has an input bit. They should compute the end of the two bits. Namely, the output is 0 except for when the two input bits are 1. So this might be useful for some applications, say for dating. If Alice is interested in Bob and he's interested in her, they should learn a 1. Otherwise, they should learn a 0. So if Alice has a 1 and the output is 0, obviously she knows that Bob's input was 0. Okay? But if Alice's input is 0 and the output is 0, then she doesn't know whether Bob's input was 0 or 1. So this is the privacy we should care about here. So this is like a basic function. And actually, Oblivious Transfer can be used to compute that function. So that's very simple. So let's call the parties P1 and P2, and P1 is the sender. So he'll set two inputs. X0 is going to be 0, and X1 is going to be A, which is P1's input bit. So if its input is 0, if A is 0, then X0 and X1 are both 0, otherwise they are 0 and 1. And P2 is the receiver, and its input is its choice input J is its input bit to the end function B. And they just run Oblivious Transfer protocol where P2 learns the corresponding bit Xj of P1. So what happens here? So the output is essentially 1 minus J times X0, because if J is 1, P2 should learn X1, otherwise it should learn X0. So it's actually equal to 1 minus J times X0 plus J times X1, because if J is 0, then the output here is X0. If it's 1, the output is 1. So this is the function they should compute, which turns out to be exactly A times B, the end function that we want to compute here, if A and B are bits. So this is the end functionality. Why is it private? So we'll just hand wave here. So if P2's input is 0, then she always learns X0, which is 0. Okay? So what she learns does not depend on P1's input A. So therefore, she doesn't learn anything about P1's input. She always learns a 0, doesn't matter what his input is. If her input, P2's input is 1, then she actually does learn P1's input A. But in this case, A is equals to A times 1, which is A times B, which is the end function, which P2 has to learn, because that's the functionality we're computing. So she learned the output, but this is something inevitable, because we want her to learn the output. And she also learns A's input because of this, but this is implied by the output if B is 1. So therefore, it's easy to derive from this fact simulation showing that this protocol is secure, at least in a semi-honest model. Now, we would like to show that it's impossible to achieve design and a protocol for computing end which is unconditionally secure. This implies that there's no Oblivious Transfer protocol which is unconditionally secure, because if there was such protocol, we could have used this transformation here, and if the Oblivious Transfer was unconditionally secure, then so was the protocol for computing the end. So if we show that there's no unconditionally secure protocol for computing the end, there's also no unconditionally secure protocol for computing the Oblivious Transfer. Okay, so let's show why this is impossible. So suppose there was such a protocol, and let T be the transcript of all messages sent during that protocol. Namely, P1 sends to P2 a certain message, gets back a different message, and so on. The record of all these messages is the transcript. The parties might use random inputs, and let's just say that the random inputs they use, the coin tossers, are just, we consider them as other inputs, and the protocol is a deterministic one. So the protocol, the input of the protocol run by the parties is the input bit, and maybe some randomness of some limited length. And this decides in a deterministic way what the parties are going to do during the protocol. Now the protocol is public. So P1 knows exactly what program P2 should be running. It knows that the program is a function of some randomness R2 which P2 should choose, and some input B that P2 has. And the same is true in the other direction. Okay, so let's see what happens. So we should do some mind game here. So suppose in some execution, P1's input is A equals 0, and the output is 0. Okay? Now, the parties have unlimited powers. Okay. Look at party B. Party B, it knows the transcript that happened between her and party 1. P2 knows what the information that was sent, the message sent between her and P1. Okay? What P2 can do, because it has can do exponential computations, she can go over all options for P1's input bit and P1's random input, and check if any one of them corresponds to the output that they, to the transcript that they generated. Namely, P2 and P1 had a certain communication. Then they had a certain output. Then P2 can start doing the following computation. Suppose that P1's input was 0, and suppose that the randomness, the R1 that it chose, was 0, 0, 0, 0, 0. I know what program P1 is running. What would be the first message that P1 would send me? I can compute it because I assume what its randomness is and what its input is, and I know the program. He would send me this message, I'll send him that message. He will send me this message, I'll send him that message. Is that equal to the communication we just had? Yes or no? If no, I'll throw it away. Now let's go to the second random string that P1 might have. 0, 0, 0, 0, up 1. Let's see what messages will be exchanged there. Okay? So P2 can do this examination because she can run for exponential amount of time. Okay. So we keep this in mind and let's see what happens. So P1 has an input A equals 0 and the output is 0. Now, if B's input, P2's input was B equals 0, the output was 0. But we don't want P2 to learn whether P1's input was 0 or 1. Okay? Now, suppose that this transcript that P1 and P2 had, okay, it corresponded, as I said here, to P1 having an input 0 and to some randomness that it had. Now P2 starts doing this mental examination, checking all options for P1's inputs. If she sees that for P1's inputs, there's no random string such that P1 will have that random string, I call it here R1 prime. So that with this R1 prime and with P1 having an input A equals 1, if P2 sees that there's no such pair of random string and A equals 1 for P1 that result in this transcript happening between P2 and P1, then P2 must decide that the only option for P1's input was A equals 0. Because she says, I saw this transcript coming from P1. Now I check all of the messages that P1 can send me for an input 0 and for an input 1, with all randomness possible for P1. If she sees that when P1's input is 1, there's no conversation that seems like the one she just received, then obviously P1's input was 0. Okay? So therefore, if we don't want P2 to be able to do that and deduce P1's input, we have to make sure that there must be some R1 prime for P1, so that even if P1 has an input A equals 1 and not A equals 0, the conversation of P1 and P2 would be exactly like the one they had when P1's input was A equals 0. Okay? So there must be identical conversations both when P1 has input 0 and input 1. This is when P2's input is 0. Now, if P2's input is B equals 1, and here I said that P1's input is 0, okay? Now, if P2's input is 1, then obviously the output must be 0, okay? Therefore, it's impossible that there will be a conversation where P1's input is A equals 1, that will be exactly the same as the conversation we had here when P1's input was 0 and P2's input was 1. Because here the output must be 0, and where P1's input is 1, the output will be 1. So let me just try to summarize. It's a bit complicated. What's happening here is that P1 had the input 0, okay? And we had a certain conversation with P2. If P2 had an input 0, then there must be another conversation of P1, which will result in exactly the same conversation they had right now. If P2's input was 1, then there cannot be another conversation of another input of, sorry. There cannot be another random string of P1 that will result in the same conversation. Okay, so this is just a mental game. Okay, now P1, is smart too, and it can do this mental game by itself. Therefore, what P1 can do, after it has a certain conversation with P2 with this input A equals 0, it thinks about this, and then it just goes over all possible values for its own random input R1, and check what happens if it runs its program with them, assuming that it had this input A equals 1. Okay? And checks if there is one random input of his that will result in the same transcript it just had when its input was 0. What I said here basically says that if P2's input was B equals 0, then P1 must find here for its input 1 some random string that will result in the same transcript. Whereas if P2's input was 1, then P1 cannot find another random string that will result in the same transcript. So therefore, P1 can just go over all of its random inputs and see whether one of them results in the same transcript for an input A equals 1. If it finds 1, then P2's input is 0. If it doesn't find 1, then P2's input is 1. So therefore, P1 that can run here for an exponential time can learn what P2's input is. Okay, so this is a bit complicated. Basically, what this mind experiment shows that we cannot hope here to have security against parties that can run for exponential time. So therefore, we must design oblivious transfer protocols that are based on some computational assumption. The protocols I show, at least in the beginning, will be based on the decision of Diffie-Hellman assumption, at least in one direction, and will have unconditional security against the other party. So against one party, we'll have unconditional security. Against the other party, security will be based on the DDH assumption. Yeah?
But you don't assume any additional setup assumptions like trusted hardware or noisy channels or some magic going on
for
that impossibility result, right? In the following, you assume just Turing machines writing on output.
Yeah, so what I showed you that if there are just 2 Turing machines, I don't assume that they have anything else like smart cards or trusted hardware or anything like that. They cannot hope to have an oblivious transfer protocol which is unconditionally secure. So actually, by showing this, I might save you a lot of work because someone might be trying to design such a protocol, and this argument shows that it's impossible to design an oblivious transfer protocol with these properties. Okay. So usually we want to design protocols which are fully secure, according to the definitions we showed yesterday, because they are efficiently composable in other protocols. However, sometimes it's better to design protocols with lower levels of security. Why is that? They might be more efficient, or it might be that we don't know how to design protocols which are fully secure. So today we know how to design such oblivious transfer protocols, but 10 years ago we didn't. Maybe 11 years ago we didn't. Okay? Actually, I think it's actually 11, not 10. So in that case, we still want to use oblivious transfer. We might design one with a lower level of security. So basically, what we can aim to achieve is just privacy, not full simultaneity, but just privacy, ensuring that the parties don't learn more than they should. So we learn that we show that they don't learn more than they should, but we don't show correctness in dependence of inputs. Namely, we don't ensure that the protocol implements the oblivious transfer functionality. It might be some other function. Okay? And we don't ensure that the inputs of the sender are independent of the input of the client and the receiver and vice versa. Okay? These are properties which are implied by the full definition, not by the privacy definition. And also, if we just use this definition, we don't have a general composition theorem. If we want to compose this protocol into a different protocol, we have to prove that this is secure. We cannot just refer to some known theorem. However, it's also hard to actually define what privacy means. For Oblivious Transfer, it's actually possible because the protocol has only 2 rounds, so the definition is simpler. So why do 2 rounds help here? 2 rounds help because the receiver sends one message and receives an answer. That's the entire protocol. So basically, when the receiver sends the first message, it essentially commits to its choice. I mean, it doesn't have another message in which it can decide to which item to choose. So if the receiver sends just a single message, basically it just says in this message, in some encoded way, I want to learn x0, x1. Okay? And this is very useful in definition in the proofs. So the privacy definition will be the following. In the case of a malicious sender, it's quite easy because the sender shouldn't learn anything in Oblivious Transfer. So what we just want to prove is that the sender doesn't learn anything about the input of the client, namely doesn't learn whether the client or the receiver wants to learn 0 or 1. So what we prove is that the sender cannot distinguish the case where it should be j here. J equals 1 or j equals 0. They should look indistinguishable to the sender. And you can extend it to many messages. If there are more options than 2, like 4 or n, you can extend this definition. How about the receiver? So here the receiver does learn an output. So we cannot say it cannot distinguish between different inputs of the sender because it does learn something from the sender. Okay? So what we try to require here is that it learns just one message and not the other one. This is what we want to catch here, right? So definition, I don't put it here in an exact way, just in a hand-waving way, is that after the receiver sends its first message, it essentially commits to learning one input of the sender, or put it more accurately, the first message of the receiver actually commits to not learning anything about one of the messages of the sender. So by sending the first message, essentially this makes sure that the receiver doesn't learn anything about x0 or about x1. But it cannot be that this first message enables the receiver to learn a little bit about both messages. It's going to learn just about one of these 2 messages. Okay. So the protocol, all protocols we show will depend on the decisional Diffie-Hellman assumption, DDA's assumption, and I'll just describe it here because I don't think we described it earlier in this school. So the DDA assumption is the assumption that the following problem is hard. We work in a certain group G of order Q, which some generate a little g, and we get a pair of tuples in random order. One contains g to the a, g to the b, and g to the c, where a, b, and c are chosen at random in the range 1 to q. And the other contains g to the a, g to the b, and g to the power of a times b, where a and b are chosen randomly in that range. And the task is to decide which of the 2 tuples is g to the a, g to the b, and g to the a times b. Okay? So in one of them, these first 2 items decide exactly what's the value of the third item, whereas here the third item is completely random. Okay? And the assumption is that it's hard to decide which of these 2 values is the right one. Going back, we also have the computational Diffie-Hellman assumption, which states that given g to the a and g to the b, it's hard to compute g to the a times b. Here we're talking about a problem which is much easier than the computational Diffie-Hellman assumption. I also give you two possible answers to what g to the a times b might be. It's either this value or this value, and your choice is to find which one of these is g to the a times b. And the claim in this assumption is that this is still hard. It might be easy to find this with probability 50%, but it's hard to find it in some better probability. And as some student told me, it's just like in exams, some questions in exams are closed form questions, where you don't have to have a full answer. You get like 4 answers: A, x equals 2, B, x equals 4, C, x is 10, and D, none of the above, right? So obviously, if you get these answers, it might be easier than trying to compute the answer for yourself, because you have 4 options already. So the computational Diffie-Hellman assumption is the open question version. You have to compute g to the AP by yourself. And the DDH version is the closed form version, where I give you 2 answers, and all you have to do is choose which one of them is the true one. But the assumption is it's still, even this version, it's hard. You can guess with probability 50%, but that's all that you can do. Okay. So now let's go to the Oblivious Transfer protocol. It's run by Monina and myself. And it satisfies only the privacy condition. It's not fully simulatable yet. So the inputs are x0, x1, and j to the receiver, and we work in some group G of prime order Q with the generator G. The receiver chooses random A, B, and C1 minus J. You see it in a minute. And defines Cj to be A times B. Remember, the J is either 0 or 1. This is the input of the receiver. And then it sends to the sender the 4 tuple g to the A, g to the B, g to the C0, and g to the C1. So if J is 0 and the receiver wants to learn x0, then it sends here g to the A, g to the B, g to the A times B, and g to the C1, which is random. If the receiver wants to learn x1, it sends g to the A, g to the B, g to the C0, which is random, and g to the AB, which is what it should do now. So these 2 items, one of them is equals g to the AB according to whether the receiver wants to learn x0 or x1. This message is sent to the sender. What does the sender do? So the first thing it does, it checks that GC0 is different to GC1, that these 2 values are not the same. Why is that? That's because here the receiver put g to the AB here if it wants to learn x0, and g to the AB here if it wants to learn x1. So it seems like if you put g to the AB in one of these locations, you learn the corresponding input of the sender. And the protocol is such that if you put g to the AB in both of these locations, you learn both inputs. Okay? So we must have the sender do this simple check just to verify that these 2 values are not the same, because if they are the same, the receiver can just put the same values, the same g to the AB, and learn both inputs of the sender. Okay, this is a simple check, but it's crucial here. Then the sender chooses random values, U0, V0, U1, V1, and does the following. So for the first item, it generates some W0, which is g to the A, this first item, raised to the power of U0, times g raised to the power of V0. And then it equips its input x0 with the following key. Key 0, which is GC0, this is this item, to the power of U0, and g to the power of b, this item, to the power of V0. Now it does exactly the same for the second item with some differences. First, here it used U0 and V0, and here it uses U1 and V1. 0, 1. Just a different set of randomness. Okay? The only other difference is that here we used g to the power of Z0, and here we used g to the power of C1, g to the power of C0 and C1. Okay? Now we call that only one of these is equal to g to the power of AB, and this is the one where decryption is possible. Okay? And since the other one is different, decryption will not be possible. Then the sender sends these W0 and W1 values and the resulting encryptions to the receiver. The receiver is supposed to compute one of the keys and decrypt. And what I say here is that the receiver can simply compute if, Wj, which is either W0 or W1, to the power of B, and this will equal to the key which it wants to use to decrypt the input. So if it wants to learn x0, then W0 to the power of B will be equal to K0. So we have to show this is true. Okay? So let's see if this is true. Okay, so suppose the receiver wants to learn x0, and so therefore it sent these messages. This is g to the AB. Now the sender defines W0, as I said, and encrypts x0 with this key, K0, which is g to the AB now, because this is g to the C0, to the power of what I wrote here, times this. Now if you look at the equation, the encryption key is exactly W0 to the power of B. Just look at this line here, raised to the power of B. This is what you get here. So therefore, the receiver can just take W0 raised to the power of B, and it gets the key, and it can decrypt. So this, magic shows that this arithmetic shows that the receiver can decrypt. So we do compute the Oblivious Transfer functionality. And what we do have to show later that the receiver cannot decrypt both items. But at least the item that it wants to obtain, the receiver can decrypt. Now I have a question there. Okay. You do have a question?
When we define W0, why do we multiply with G to the B0? Is that needed?
Oh yeah, it is needed. Okay, let's see what happens if we don't multiply by G to the V0. Let's wait with the proof, and then, so of course it's not needed for being able to decrypt the item that you want to decrypt. It will be needed to make sure that you cannot decrypt the other item. But let's wait to the proof, and then we'll see why it's needed. Okay, what's the overhead? So the receiver had to compute these values, these 4 exponentiations here, and 1 here for the decryption, so it's 5 exponentiations. And the sender had to do 2 exponentiations here, 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 and here, so it's a total of 8. So 5 and 8, it's not that good, it's not that bad. This is about the range in which we'll stay. Now privacy. What happens with a malicious sender? We don't want the malicious sender to learn which item the receiver wants to learn. So it's based on the DDH assumption. We must show that whatever the sender sees is independent of the receiver's input. So the sender sees either G to the A, G to the B, G to the A, B, G to the C, in case the receiver wants to learn X0, or a similar tuple but with the order of G to the A, B, and G to the C reversed if the receiver wants to learn X1. This is what the server sees. And we want to show this is impossible. It's impossible to distinguish between these two cases, right? So we should show that if this is possible, we can also break the DDH assumption. So suppose there was a sender that can distinguish between these two distributions. So we can use it to break the DDH assumption. We get an input to the DDH problem, and we can use the server, the sender, to help us answer. How do we do that? We get these two tuples in random order. One has G to the AB and one has G to the C. Okay? What we do, we generate a message to be sent to the server, which is going to contain the G to the A and G to the B, which we received. And then these two third items that we receive, we put them to the server in random order, either this one first and the other one second, or in a different order. Now, if the server can distinguish between the case that the G to the AB comes before the G to the C, or vice versa, we can use this fact to tell whether it tells us whether the third item we put was g to the AB or the fourth item we put was g to the AB. We know that the third item is the one that we took, say, from the first tuple that we received. So therefore, we know which tuple had g to the AB in our input. So if the server can answer correctly the question we give him, we can answer the DDH query that we received. Okay. So therefore, the server cannot distinguish between the two options of the client's input unless it can break the DDH assumption. Okay. Now, what about the malicious receiver? So a malicious receiver would try to learn about more than a single value. Okay? And here we'll show that it's impossible. Actually, this proof does not depend on any computational assumption. We show that no matter how strong the receiver is, it cannot learn anything about more than a single input. So let's see how it works. Suppose now the receiver wants to learn the first item, x0. So what happens about x1? The server receives, actually the receiver should see, this would be a receiver here. So the receiver sees this W1 computed like this, and X1 computed with this key, with some G to the C here, where C is different than A times B. Now what's important that U1 and V1 were chosen at random. What we show in this claim, we'll prove in the next slide, is that W1 and K1, which I show here, are uniformly random. Okay? So basically what the service, what the receiver sees is a random W1 and an encryption of X1 with a random key, which is independent of this W1. So if you get an encryption with a random key and some other random string, obviously you cannot decrypt the message. Okay? Because it's just, it's random. Okay? So this is true if this encryption is with information theoretic security, like a one-time pad or anything of that sort. Okay? So if the key is randomly uniform, and the same is true for the other message you receive, obviously you cannot decrypt. Okay. So let's see why this is true. So this is W1, this is K1. And if we look at the equations, W1 is G to the A times U1 plus V1. And K1 is this function. So we have G to C over B times U1 plus V1 to the power of something. Now look, this function is almost like this. It's something times U1, something times U1 plus V1, right? So let's define a function f of x, which is U1 times x plus V1. Just notation, right? So since we choose U1 and V1 at random, this is a random linear function which is pairwise independent, meaning that for every two inputs, the two outputs are uniformly distributed. Okay? So what are W1 and K1? W1 is G to the power of FA, and K1 is G to the power of F of C over B to some other power. Now, if C is different than A over B, then C over B is different than A. So here we have G to the power of one thing and G to the power of a different thing. G to the power of F of one thing and G to the power of F of a different thing. And since we said that F is pairwise independent, these two F values are uniformly random. Okay? So therefore, this and this are uniformly random. Here we raise it to the power of B, but it's still random. Something random to the power of B is still random. So unless C is equals to A times B, which we check that this case does not happen, we get here two random outputs. So in this case, the key is random and P2 doesn't learn anything. So according to your question before, so you ask why we use this V1. So if we didn't have V1 here, then the function we had up here would be just G to the power of A times U1, and the same here. So F wouldn't be U1 times X plus V, but rather U1 times X. So in that case, it won't be a pairwise independent function. Okay? It would be a line, but a line that crosses the origin of the two axes. right? So in that case, we cannot claim pairwise independence anymore. So it's nice, actually, it's nice when you have a construction and you have a proof, you have to look at the end to make sure that all the items in the construction were used in the proof. Otherwise, something in the construction is missing or the proof is wrong. Something in the construction, I mean, either you added too much to the construction or your proof is wrong. Okay, so that was an Oblivious Transfer protocol where we only ensured privacy. We ensured that nothing is learned, but we didn't ensure simulation. We didn't ensure this is the Oblivious Transfer function. Now we want to ensure simulation. To do simulation, we'll do it in 2 steps. First, we'll show one-sided simulation, and then we'll see full simulation. One-sided simulation is basic simulation just against one party. We'll be able to simulate the input of one party, but not of the other party, and then we'll do the next step. Okay? So what we will require is that there will be a simulator that can fully simulate the receiver's view. Basically, we show that whatever the receiver does here, it can also do in the ideal model with a trusted third party. We don't do this yet for the sender here. So therefore, we don't ensure that the sender's input, say, doesn't depend on the receiver's message or anything like that. But this will be done in about 10, 15 minutes. Okay. So we can take the previous protocol I showed and convert it very easily to a protocol with one-sided simulation against a corrupt receiver with just a single modification. The receiver sends exactly the same message as before, but in addition, it sends a zero-knowledge proof of knowledge of A, namely of the discrete log of the first item here, G to the A. Okay? Now, we just learned about zero-knowledge proofs of knowledge in the previous lecture, so we know that they're efficient. Okay? So we just add this step before we do our protocol. So why is that good? So intuitively, this means that the receiver knows the discrete log of G to the A. So if you know the discrete log of G to the A, and you know what G to the B is, you know whether this equals G to the A times B, or this is G to the A times B. Right? If you know A, you know G to the B, you can easily compute G to the A times B. So then you know which one of these is G to the A times B, so therefore you know what's the input that the receiver wants to learn. So intuitively, this means that the receiver knows which input it wants to learn. So therefore, we can simulate it and so on. So let's see how it goes here. So, okay, we add these zero-knowledge proofs of knowledge. It's an additional 9 exponentiations and 6 ones of communications, the last one of which can be combined with the first one of the Oblivious Transfer protocol because they go in the same direction. And the security proof will have the following line. There is this zero-knowledge proof of knowledge of the discrete log of G to the A. We'll have a simulator which will extract A from this proof of knowledge. So therefore, we'll know what the simulation will know what A is. So we'll know this value. Okay. Now, if we know what A is, we can check for ourselves as a simulator which one of the third and fourth items is G to the A times B. If we know that, we can send us input. We call this value J, which is either 0 or 1. We can send it to the trusted party, receive xj, and now we have to simulate what the receiver sees in the real protocol. We receive xj from the trusted party. We can encrypt it to the receiver, and the other value we don't have to care about because the receiver cannot decrypt it anyway. Because in the Oblivious Transfer protocol, the receiver can only decrypt one value. This is just the intuition we have. So we extract from the proof of knowledge which item the receiver wants to learn. We ask the trusted party what's the actual value of that value. And then we follow the Oblivious Transfer protocol, encrypt that value, and just send an encryption of an arbitrary value instead of the other input of the sender, because the receiver is not going to learn that anyway. Okay, so here's the proof. So the case of a malicious sender is just as before. So before recall I showed it, no, that the DDH assumption implies that the sender doesn't learn anything from the message it sees. Now the sender, in addition, also sees a zero knowledge proof of knowledge. But the zero knowledge property implies that the server doesn't learn anything from this zero knowledge proof of knowledge. And from the message it learned before, it also doesn't learn anything. So that's it. Now what about the malicious receiver? So a malicious receiver, okay, we have to show a simulator that interacts with the receiver and simulates what the receiver sees in the real protocol. So look at the malicious receiver, R star. The simulator gets from the receiver the first message and the zero knowledge proof of knowledge of discrete log of g to the a. Now it runs the simulator we have for the proof of knowledge and extract a from the proof. Okay? So now we know what a is, what's a discrete log of here. So therefore, now we can check whether the third item or the fourth item is equal to g to the ab. If it's the third item, we say that j is 0, otherwise we say that j is 1. We send j to the trusted party, and we get back xj. Now we return encryptions to the receiver exactly as in the protocol. So the xj we encrypt as in the protocol, and the x1 minus j we don't know because we only ask the trusted party for one value. So we just say, okay, let's say that x1 minus j is 1, say, we encrypt it and hope that the receiver doesn't notice that we put the 1 instead of the actual value of x1 minus j. Okay, so let's see what happens with the receiver's view. So actually the receiver sees exactly the same things until the last message. Okay? And in the last message also everything is the same except for the encryption of x1 minus j, which we replace the actual x1 minus j with 1. That's the only change we did from the receiver's point of view. Okay, that's the only change. But a few minutes ago, we proved that for, a few minutes before we proved that if, for GC up here, which is different than G to the AB, the receiver cannot learn anything about the encrypted message. Okay? So what we proved earlier was that of the two messages, one the receiver can decrypt, and the other one is uniformly distributed. Okay? So if we go here, since the receiver knows, okay, since, say, C0, the third item is G to the AB, therefore the fourth item is not G to the AB, therefore the receiver cannot learn anything about the encryption using the fourth item, namely, say, the encryption of X1. So therefore we can replace X1 with any item we want, and the receiver won't be able to distinguish the encryption of that item from the encryption of the actual X1. Okay? So that's here, we're done. The view that the receiver does is exactly like in the original protocol, except that we replace one encryption of an item with an encryption of a different item. But we showed before this encryption is one in which the receiver doesn't gain any information about the encrypted value. Okay. So this was a protocol with one-sided simultaneity. We want to also to simulate the view of the other party of the sender. So why isn't the previous protocol I showed good to simulate the view of the sender? Okay. So to simulate the view of the sender, what we usually do in proofs, we try to write a simulator which will somehow extract the actual inputs of the sender from its messages, give it to the trusted party, and then continue the protocol. Now, in the protocol I showed, the sender receives this message, G to the A, G to the B, and G to the C0, G to the C1. And I argued that if G to the C0 is G to the A times B, it's an actual encryption, but if it's different, we learn nothing about the encrypted value. Now, since the sender checks that the third and fourth item, G to the C0, G to the C1, are different, only one of these is equal to G to the AB. So therefore, the item encrypted with the different, let's say if the third item is G to the AB, then the encryption which uses the fourth item is uniformly distributed. We cannot learn anything about the encrypted value there. Okay? So therefore, we won't be able to extract anything about the value encrypted using the fault value. Okay? So we're stuck there. We cannot, if we send a message of this type, we might hope to extract information about one of the sender's inputs, but not about the other input of the sender. So we cannot just work like this. So another option we can think of for the simulation is the following. Let's send the sender a message of this type, say where the third item is G to the AB, and then we'll be able to extract the item encrypted with the third item, say X0. Okay? Then we rewind the execution, go back one step, and send the sender another 4 tuple G to the A, G to the B, G to the C, G to the C. But now we'll put the fourth item to be G to the AB. Okay? And now we'll be able to extract information about the second input of the server, about X1. Okay? So we'll do one run where we put, say, G to the AB here, and a second one where we put G to the AB here. And then we'll be able to extract information about both of the sender's inputs. Okay? So this seems nice, but there's a problem here. In the first one, the server sees one tuple, the one up here. And the second one, it sees a different one here. It might be that the server, which might be corrupt, decides on the messages that it wants to send us, depending on the message that it itself received. It might be that if it received the first message, it decides, okay, x1 is 0 and x0 is 20. And if it sees the second message, it says, okay, x0 is 100 and x1 is 200. Okay? So we will extract values out of different pairs of messages in the two executions. Okay? We have to make sure that the sender sees like the same uniform view in both tests that we do. So basically, we have to replace this with the message that enables us to extract both inputs of the server. Okay. So a protocol doing that was suggested by Kermit Chazai and Yehuda Linden, and I describe it. And first, the idea behind the protocol. So the idea is the following. Say that the receiver sends a longer message. So 2 tuples as before, but instead of 1 tuple, it sends 2 tuples. And it will also prove that he's sending here 2 tuples, but are they going to be used only for learning one input of the sender? So what suffices here to say is that either C0 up here is AB, or C1 prime here is A times B prime. But it doesn't show that both of these hold. Okay? So why does it suffice? If C0 is A times B, then in the first tuple, the sender can learn X0. It cannot learn X1 because here the receiver can learn X0. It cannot learn X1 here because here the sender checks that these two values are different, so it can only learn one of these values. Now, if C0 is A times B, then C1 prime cannot be A prime times B prime. So therefore, in this second tuple, the server cannot learn X1. It might learn X0, but not X1. So overall, it learns X0 here, but it doesn't learn X1 here, and here it cannot learn X1, so it only learns X0. And the same holds if C1 prime is equals to A prime times B prime, the sender learns X1 in the second tuple, and maybe also in the first tuple, but not in both of them. And this is a zero-knowledge proof of knowledge that we can do. So suppose this is what we do. So the protocol is again the receiver can only learn one item. Now in the simulation against the malicious server, what we can do, we can cheat in the zero-knowledge proof, and somehow send messages where both of these values hold. Both C0 is A times B, and C1 prime is A prime times B prime. So in the simulation, we'll send these corrupt strings, we'll cheat in the zero-knowledge proof, and therefore we'll be able to extract both inputs of the sender, give them to the trusted party, and be able to continue the simulation. Okay? And what's good here is that we only have one message, although of double length, and we'll be able to use it to extract both inputs of the receiver, of the sender. So if we think about my previous slide, I said like that. If the receiver sends a single message, it's going to be used, it can be used to extract just one input of the sender. And if we rewind and go back with a different message, the sender might behave differently. So the solution, according to this idea, is the following. The receiver is going to send two messages at the same time, but it's going to prove that these two messages do not enable the receiver to learn more than one item. They have redundancy. They both enable to learn the same item. Okay? So therefore, the actual run of the protocol is still going to be secure. In the simulation, though, the receiver is going to cheat, because simulation we can cheat, and the proof will seem okay, but the message will actually not be okay. They're enabled to learn both inputs of the sender, therefore we can continue the simulation. Yeah?
But what if the sender's OT message depends on the zero-knowledge proof scheme? How do you implement that? Or is it a non-interactive zero-knowledge proof?
That's a good point, but it is a non-interactive.
It doesn't matter, because the sender's message comes after the zero-knowledge proof is complete, and you can extract from that message both values. You're not doing it twice at different times, you're doing it at one shot, so you get the correct distribution.
Okay, so what you just said was that the sender's message comes after the zero-knowledge proof, and therefore, regardless of what happened during the zero-knowledge proof, you can still extract from this single message of the sender both inputs of the sender. Okay, but that's a nice question. Okay, so this is the idea, and this protocol actually works. Now the question is how to do it more efficiently. Okay, so this is like as a methodology. This is the way we will go. We just do it more efficiently. So this is the protocol, or this is the idea of the protocol. The sender, instead of sending 2 4 tuples, it's going to send 1 5 tuple of this form. A0, which is G to the A0, H1, which is G to the A1, D, which is G to the R, B0, which is G to the A0 times R plus J, and B1, which is G to the A1 times R plus J. Now recall that J is just going to be either 0 or 1. Okay? Now, if J is 0, then the triplet H0, D, and B0 is a DDH tuple together with G. If J is 1, then the pair H1, D, and B1 over G is a DDH tuple. Why is that? Because if J is 1, this is B1 is GA1 times R plus 1. And if we divide it by G, we get G to the A1 times R. Okay? We see that, we get 2 different DDH tuples, so we'll be able to somehow use each one of them to encrypt a different message. We also need to make sure that the receiver cannot decrypt both messages, namely to make sure that it can be that both of these pairs both of these triples are DDH tuples. So in addition to sending this message, the receiver must prove that it's not true that both these tuples are DDH tuples. So to prove that, it's sufficient to show that H0 over H1, D, and B0 over B1 is a DDH tuple. Basically, if this is true, it cannot be that B0 is G to the A0 times R, and B1 is G to the A1 R plus 1. Because if these two hold, then when I divide B0 by B1, the R, I don't get the DDH tuple together with these values. Because this plus 1 I had here in B1 doesn't cancel out, doesn't look like what you need to have in the DDH tuple. So here, by just proving that one tuple is DDH, I prove that it cannot be that the 2 original tuples are both DDH. And this is what I need to show here. Okay. So, okay. If we do this proof, then when j is 0, one tuple is DDH and the other isn't, and if j is 1, the other tuple is DDH and the first one isn't. Therefore, I'll use the first tuple to encrypt x0, the second one to encrypt x1. Okay? So here's the protocol, like with just putting everything together. The receiver sends this 5 tuple, then it proves a zero knowledge proof of knowledge that this tuple there is a DDH tuple, which implies that it cannot be that the two tuples I described earlier are both DDH tuples. Then we do encryption as in the original protocol, using these tuples, and the receiver decrypts. So this is exactly like in the original protocol. So correctness, okay, I'm doing here calculations, but it's just arithmetic, okay? So you get these values. If you do the math here, you see that if you take W0 and raise it to this power, you get what you need to get, namely the key in which the values are encrypted. Okay? So you don't gain a lot by going over this together here in class, but if someone wants to be convinced, you just do the arithmetic yourself. What about overhead? So the total protocol is going to take 6 rounds of communication, including the zero knowledge proof of knowledge. The server computes 15 exponentiations, and the receiver computes 11, which is not very little, but not very much. Okay? So it's not very bad, and I'll say later what happens if you need to compute many of these oblivious transfers. Okay. What about security? So how do we actually handle a malicious sender? This is what we try to handle using all this, using this fancy protocol we have here. So in the simulator, we want to be able to extract both inputs of the server. So what we do is we send the tuple as before, but in the original protocol, we remember that either B0 and B1 should have used j equals 0, in which case they didn't have a +1 at the end, or they should have used j equals 1, in which case both of them had a +1 at the end. Okay? What we do in the simulation, we use some hybrid in between, where one of them is just like the one we would have sent if our input was 0, and one of them is just like the one we would have said if our input was 1. Okay? So we're sending this hybrid. Okay? So this is what happens in the real execution. This is what we sent here. Now, of course, what we sent here is not something that one can prove to be correct in the real protocol, but since we are in the simulation, we can rewind the proof back and prove false statements as if they are correct. So therefore, we prove to the poor sender that this is a tuple like the one it should see in the protocol. Okay? Now, when the sender sees this, he gives us back 2 encryptions. And what happens is that we can decrypt both of these encryptions. Because if you follow the math, you can compute K0 by this equation and K1 by this equation, and it just works. You just have to combine the equations we had for the 0 and 1 versions of the original protocol. So if we decrypt these values, we learn the 2 inputs of the sender, we send them to the trusted party, and we can continue the protocol in the simulation. So the only difference the sender sees between these messages and the original protocol is the first tuple. So in the real protocol, if j was 0, he saw this tuple where we only had zeros here. If j was 1, we had this tuple where we had +1s. And here he gets a tuple where one item doesn't have a +1 and the other one has a +1. So it's not hard to see that basically this boils down to the DDH problem. And if the server can distinguish between these cases, it can also solve the DDH problem. This is just a standard reduction to DDH. Now, what happens in the case of a malicious receiver? So we do a simulator where the idea is, okay, we need to know what's the input of the receiver. So we get the tuple from the receiver. we should extract from the tuple, from the zero knowledge proof, information about which item which item the receiver wants to know. So what we can do is to extract the R, which is a discrete log of D. Namely, if D is G to the R, we learn what R is. Then it's easier to learn whether B0 here is H0 to the power of R or H0 to the power of R plus 1. If it's H0 to the power of R, then the receiver attempts to learn X0, otherwise attempts to learn X1. And according to this, we send input to the trusted party, learn back an input of the sender. Now when we send back a message to the receiver, we encrypt that value received from the trusted party as an input of the sender, and replace the other input of the sender with, say, a 1. And just as before, it's possible to show that the receiver can only decrypt one of these values, which is actually only the one for which we got the value from the trusted party. So that value the receiver will be able to decrypt, and the other one it will not be able to decrypt. So this is shown here, but it follows the ideas we had previously. Okay, so let's try to conclude. So we showed here a fully simulatable Oblivious Transfer protocol, which is rather efficient. And this is useful because once you believe this, when you use Oblivious Transfer in other protocols, you don't have to think about how Oblivious Transfer is implemented and how to prove the more complex protocol you're using. You can just say, my complex protocol uses Oblivious Transfer as an oracle. I have an oracle which computes Oblivious Transfer for me. If you want to do many Oblivious Transfers, it's actually possible to do this more efficiently. So the overhead can be reduced for something like only 14 exponentiations per Oblivious Transfer, plus more exponentiations for the initialization. Because what we did here, we sent a tuple and proved it to be of the right form. If you're doing many Oblivious Transfers, you can essentially do a single proof in the beginning, or part of the proof you can do once, even though in different Oblivious Transfer you're learning different items. And you have to do less for every Oblivious Transfer. Now there's another protocol that does Oblivious Transfer, fully secure Oblivious Transfer in this model, protocol by Pinkas, by Kuntanathan, and Waters, which uses similar ideas but different techniques. And it's actually more efficient than this one. So you see in the batch version, here we use 14 exponentiations per Oblivious Transfer. Here it uses 11 exponentiations. And the initialization is also more efficient. Now, the reason I showed you the protocol that I showed you is that because there's like a nice gradual learning where you start from a protocol which is only private and you go to the protocol which is fully simulatable. The other protocol, the PVW protocol, it might be harder to explain in this gradual way, but it's more efficient, slightly more efficient. Now, we only consider the standard model. You can do more efficient Oblivious Transfer if you're willing to use a random oracle, or if you don't need the full notion of simulatability, but you have to be careful if you resort to using such protocols. Another interesting or useful idea about Oblivious Transfer is extending Oblivious Transfer. This is original work of Beaver, which was more theoretical, and then much more efficient protocols of Yuval Ishai, Kilian, Kobi Nissim, and Erez Petrak. And there the idea is the following. If you want to do many Oblivious Transfers, you first compute K of these, where K is some computational security parameter, or maybe statistical security parameter, I'm not sure. Computational security parameters, say K is 128. And then you can do essentially as many Oblivious Transfers as you want for free. For free meaning just doing private symmetric key operations and exclusive ORs. So you pay in the beginning to do, say, 128 Oblivious Transfers, and then the rest you get for free. So this is very, it's very attractive. You have to, you can basically do Oblivious Transfer for free as long as you're doing more than 128 of these. It's very attractive. The problem is that I don't know of a proof of these techniques which are secure in the sense of full simulatability. Okay? So if you're using these techniques, you have to be careful when you try to prove the protocol in which you use Oblivious Transfers. But of course, this is much more efficient than the protocols I described to you. It would be very interesting to combine these two ideas. Okay. So this is what I had to say about Oblivious Transfer. And do you have any announcement to make?
Yeah,
just any questions first? Okay, so announcements.
we're going to take a photo of everybody before lunch. So everyone goes downstairs and waits outside before we go into the lunch room. We'll take a group photo of everyone and then we'll have lunch.
I didn't brush my hair.
Lucky we're registered.